Hello, this video is on chapter 9, sections 9.3 to 9.5. This is about acid, base, and strengths first. I want you to take out your yellow packet of reference and go to page 5 of that yellow packet. And the page 5 is all dedicated to acid and bases. And so I have this page open. So there is a table there with a list of acids, and if you look at their formulas, they are made of hydrogens, halogens, sulfur, nitrogen, oxygen, phosphorus, carbon, which are all non-metals. And so acids are covalent compounds because they are made of non-metals only. However, they behave like if they are they behave like ions in solution. For example, HCl, when you place it in water, it dissociates into H3O plus and Cl minus. And so remember how an acid-base reaction is having an acid that donates a proton. So HCl here is the acid. It will donate a proton to the water, and water will act as a base. So when the proton leaves HCl, it leaves behind Cl minus, right? The negative charge comes from the fact that HCl donates an H plus. The H plus goes with the water and forms the H3O plus ion, the hydronium ion, right? When you add H plus to this formula, it becomes H3, and the positive charge from the proton gets into the H3O plus. So HCl is a strong acid, which means it's a strong electrolyte. If you remember what a strong electrolyte, it means that it completely dissociates into water into ions. So when you place HCl in water, it completely dissociates into H3O plus and Cl minus. And this is shown by the single arrow going from left to right. There's no other arrow going backward. And that arrow, single arrow pointing to the right, is indicating a complete reaction. And that's what happens when you have a strong electrolyte. It completely dissociates into ions and then can conduct electricity strongly. And if you look at the modeling here that is representing HCl to the left, you see the chloride ion. It's the big green balls, and then you have water, and water is in the background, and then the molecules you see with the oxygen and the three hydrogens are the hydronium ion, and they float around with the chloride ions, and there is no HCl molecule anymore. It's all completely dissociated. In opposition, a weak acid is a weak electrolyte. A weak acid like CH3COOH, this is the acetic acid here. That's a weak acid, and when you place it in water, it dissociates into H3O plus and the acetate ion. Because the acetic acid, when it donates a proton, H plus, goes with H2O, and H plus plus H2O makes the hydronium ion, H3O plus. And then the acetic acid, when it loses its H plus, it becomes the acetate ion. So acetic acid is a weak acid because it's a weak electrolyte. And if you remember what a weak electrolyte is, it's a molecule when dissolved in water that only dissociate partially in water and make a small amount of ions. Here, only a small fraction of this acetic acid is making the acetate ion and the hydronium ion. So you have few ions, and the proportion of acetic acid is still very large. And because it's neutral, it's a neutral molecule, it cannot conduct electricity. And that's why it's weakly conducting electricity, because there's few ions in solution. If you look at the model here on the right, you see a lot of acetic acid molecules, and then there is only 2 acetate ions and 2 hydronium ions. And so out of a total of 11 molecules shown here, you have 4 ions over 11 particles, which shows that you cannot conduct electricity strongly because the proportion of ions is small. And that's what a weak acid is. And the key to recognize a strong acid versus a weak acid is in the arrows of the chemical equation. For a weak acid, you have a double arrow, an arrow that shows it dissociates, and a reverse arrow that shows that it stays as an acid in water and it is not dissociated. And so that double arrow tells you it's an equilibrium and you still have a lot of acid not dissociated. It's the same principle for bases. A strong base is a strong electrolyte. In water, 100% of the base will dissociate into ions. So for the bases, you need to know that all strong bases will have the hydroxide ion in their formula. For example, NaOH, there is the Na plus ion and the OH minus ion. The OH minus ion is called the hydroxide ion, and any ionic compound made of the hydroxide ion and an alkali metal or an alkaline earth metal will make a basic compound, a base. And the reason why those alkali metal and alkaline earth metals are called like that, it's precisely because they make compounds that are basic. Know that basic is synonymous to alkaline, when the word alkaline means it's basic. So the alkali metal and alkaline earth metals are making basic compound, especially even strong bases if they are associated with the hydroxide ion. Anyway, so when NaOH, which is a solid because it's an ionic compound, typically they are solid in by themselves. When you place it in water, it will dissociate into Na plus and then the hydroxide ion, OH minus. And notice here the arrow is arrow going to the right, and there is only one arrow. So it's a complete dissociation into ions. And that's why it's a strong electrolyte, because now it's only a mixture of ions that can carry the electricity. And if you look at the model on the left here, you see the gray balls represent Na plus and then the OH minus, and that's only what you see. There is no NaOH. So that's a strong base. Now, a weak base is a weak electrolyte, and that means only a small fraction of the base will dissociate into ions. The example here is ammonia. Ammonia by itself is a gas. When you place it in water, it will dissociate into the ammonium ion and the hydroxide ion. Because ammonia is a base, it will accept the proton from water. And when it accepts a proton, it becomes NH4 plus. And water will act as an acid in this case and donate its proton. And when H2O loses an H plus, it becomes OH minus, right? You can see that if you add H plus and OH minus together, the positive and negative charge cancel, and then you have H2O. So here again, the key to recognize a weak electrolyte is the double arrow that shows that it's an equilibrium, it's not a complete reaction. And so the bottom arrow going backward shows that this side is even happening more strongly. So it's only really a small fraction of the base that dissociates into ions. And that's why it's a weak electrolyte, because it's only a small proportion of ions, and a large proportion of the NH3 is not, it's a neutral molecule, so it's not able to conduct electricity. If you look at the model on the right side here, you can see it's mainly NH3 molecules, and then you have two OH minus and two H3O plus only. So these ions will carry the electricity, but they are too few, so they will weakly conduct the electricity. This table is in your yellow packet. It's the same table. On the left side, it lists the acid, and on the right side, it's their conjugate base. So if you want to see conjugate acid-base pair, you read a row. And for example, hydroiodic acid, HI, its conjugate base is the I minus ion, which is the iodide ion, right? So the only difference between the acid and its conjugate base is an H plus, right? The acid has the H plus included in its formula, and the conjugate base doesn't have the H plus in its formula. And so if you look on the left side here, you can see that the acidity is increasing from bottom to top, which means that on the top of the list are the strong acid. And then as you go under the hydronium ion, it's the weak acids. And so there's only a few strong acids: hydroiodic acid, HI, hydrobromic acid, HBr, hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3, and the hydronium ion, H3O+, which has water as its conjugate base. When you look below that, all the other acids are weak. Phosphoric acid, hydrofluoric acid, acetic acid, carbonic acid, the ammonium ion, hydrocyanic acid, and water is a very weak acid. Notice how hydrofluoric, HF is the only halogen that makes a weak acid. All the other halogens are making strong acids like HI, HBr, HCl. And so on the conjugate base side, there is only one strong base, and it's the hydroxide ion. So it doesn't clearly say that on this table, but all the others are considered weak bases. And the hydroxide ion is the only strong base. Of course, it's not found by itself. In general, it's associated with the alkali metal, like Li, lithium, sodium, potassium, rubidium, cesium, and francium. And then it's also associated with the alkaline earth metals like beryllium, magnesium, calcium, strontium, barium, and radium. And so all of these will make strong bases because they are associated with the hydroxide ion. So this is part of your practice problems. If you have the practice problems paper with you, it's practice problem number 5. So you can pause and listen to the rest once you have tried to solve the problem by yourself. So identify each of the following as a strong or weak acid or base. So you need to decide first if it's an acid or a base, and then if it's a strong or a weak acid or base. So HBr is a strong acid. It's an acid because it has an H as a first in the formula. And if you look at the table on page 5 of the yellow packet, you will see that HBr is listed there as a strong acid. HCN, that's the hydrocyanic acid, is listed in your table as a weak acid. We know it's an acid because it has H as first element in the formula. NaOH. NaOH, there is no H as first in the formula, so it's a base. And you need to recognize here that there is the OH minus ion, the hydroxide ion. And the hydroxide ion, I just said, is the strongest base and the only strong base. So NaOH, sodium hydroxide, is a strong base. H2SO4. H2SO4 is having hydrogens first in its formula, so it's an acid. And if you look in the table, it's listed as a strong acid. Cl minus. Cl minus is the chloride ion. Do you see an H there? No. So Cl minus cannot be an acid. It's a base. And if you look in the table, it's a weak base. It's the conjugate base of HCl. HCl is a strong acid. And typically when you have a strong acid, the base will be weak. And vice versa, when you have a strong base like OH minus, its conjugate acid will be weak because the base is strong. And the conjugate acid of OH minus is H2O, and H2O is definitely a weak acid because it's also considered a weak base. It can act as both. And maybe you remember that we call this substance amphoteric when they can be both an acid and a base.